All right, this is homework number 4. The directions for the first part say use the graph to determine the limit and discuss the continuity of the function. So for this first one, we want the limit as x approaches. It says c from the right. C is equal to 4, so I'm going to write 4 from the right of f of x. Again, it's a good idea to write this out again so that you know you're in the habit of writing correct limit notation. The limit as x approaches 4 on the right, meaning this, is equal to 3. Part B is the limit as x approaches 4 from the left. That is also 3. Therefore, the limit as x approaches 4 from both sides of f of x is also equal to 3. Discuss the continuity. So just use the definition of continuity here. So f of 4 is equal to 3, which is also equal to the limit as x approaches 4 of f of x. Therefore, f of x is continuous at x equals 4. That's the definition of continuity at a point. All right, the next graph. So same 3 limits. So we want the limit as x approaches 3 this time from the right of f of x. That limit is equal to the intended y value, or what we're getting arbitrarily close to, which is showing us 3, 0. So that limit is 0. The limit as x approaches 3 on the left of f of x is also 0. Therefore, the limit as x approaches 3 from both sides of f of x is 0. However, f of 3 is equal to 1, and the limit as x approaches 3 of f of x is equal to 0. So therefore, f of x is not continuous at x equals 3. F of x is continuous everywhere else. It's just where we have this one point where the limit value is not equal to the function value. But if you would ask me about the limit is f continuous at 2 or 6 or 4 or any other point but this one, that answer would be yes, f of x is continuous there. So you do have to specify where the discontinuity is. I believe it's the same, 1 through 6. So same directions for number 4. So for part A, the limit as x approaches negative 3 from the right of f of x. So this way, the intended height of this graph is 3. The limit as x approaches negative 3 from the left of f of x is also equal to 3. Therefore, the limit as x approaches negative 3 from both sides of f of x is 3. Same situation as the last one, though. F of negative 3 is equal to 4, and the limit as x approaches negative 3 of f of x is 3. So therefore, f of x is not continuous at x equals negative 3. I believe we're just finding the limit for this next one. So find the limit as x approaches 5 on the right. Now we can simplify this a little bit. So first off, let's go ahead and say, well, this is equal to the limit as x approaches 5 on the right of, if I factor this out, you don't want to get 0 over 0 when you plug 5 in because that's indeterminate. So if I simplify this, the function can really just be written as 1 over x plus 5. And if I plug 5 into that, I get 1 over 10. It doesn't matter if you're approaching 5 from the left or the right on this one. You can just use direct substitution, and as long as the only time left and right matters on this is if you use substitution and you get an unbounded limit, you want to know which direction you're headed. Is it going to infinity or negative infinity? So in this case, the answer is 1/10. Same with number 11 here. If I plug in negative 3, I do get negative 3 divided by 0. the question is, are you getting a positive 0 or a negative 0? What does that mean? It's like, well, if you plug in something close to -3 but not quite, this x squared will minus 9 will either be a positive or a negative decimal. But keep in mind, you can only plug in numbers out of the square root. You can only get a positive value, right? So it's a -3 over a tiny positive decimal. And so that's going to go to -infinity. So this limit, am I saying it's equal to -infinity? Again, have we done these infinite limits yet? I suppose not. So, excuse me. So let me see how I make sure I'm answering this consistently. -infinity. Okay, so for now, we're just going to say, let me unbox that answer. So this limit does not exist. X over square root of x squared minus 9 is unbounded. We're just getting more specific. We'll do more of this tomorrow. Unbounded in the negative direction at x equals -3. Find the limit as x approaches 3 from the left of f of x, where f of x is equal to this. So this is a piecewise function where to the left of 3, we're on this graph, and to the right of 3, we're on this graph. So we're doing the limit on the left, so choose the left piece. So I want the limit as x approaches 3 from the left of x plus 2 over 2. Just use direct substitution, so plug 3 into that, and you get 5 over 2, and that's it. That's the function height, or the intended value, as you plug in positive 3. Number 19 says, find the limit as x approaches 1, where f of x is this piecewise function. And it doesn't tell me which side, so I need to evaluate both sides. And if the left and the right limits match, then I have my limiting value. If not, it does not exist. So again, show this work with the proper notation. So the limit as x approaches 1, I'm just going to start on the left. The left, this piece of the graph is to the left of 1, so the expression would be x cubed plus 1. When you plug 1 into that, you get 2. And then the limits as x approaches 1 on the right would be the other piece, x plus 1. That's also equal to 2. So the limit as x approaches 1 of f of x in general, no matter which piece you're on, is equal to 2. For the next section, we are supposed to discuss the continuity of the function. So we have a function here. We can see the graph of the function. Looks like a line with a hole in it. And that hole is a discontinuity. So I would say f of x is not continuous. You could probably say discontinuous. I don't know. Not, I think I'm spelling this wrong. Continuous at x equals -1. Because f of -1 does not exist, or there's a hole in the graph at -1. Find the x values, if any, at which f is not continuous. Which of these discontinuities are removable? Remember, removable is just a hole in the graph. Non-removable would be a vertical asymptote. So find the x values where f of x is not continuous. So factor f of x, if possible. So before I do any canceling out, f of x is not continuous or discontinuous, has discontinuities at whatever, at x equals plus or minus 6, which are removable. So the one that canceled out is the one that's a hole. So there's a vertical asymptote at -6. There's a hole at +6. So x equals 6 is a removable discontinuity. It was removed from the, I always think of it as like it was removed from the expression when I simplified it. Not that it's gone. It's just we could rewrite f of x to fill that hole in. We can't rewrite f of x to fix the discontinuity where the vertical asymptote is. All right, remember we saw this graph on, I think, our first textbook assignment. On this one, at -7, there would be a break in the graph. To the left of -7, you would get -1 every time you put numbers into this. To the right of -7, you would get +1, but there's no point at -7. So there is a discontinuity. F of x is discontinuous at x equals -7. You can't fix a jump in the graph like this, so there are no removable discontinuities. I'm probably spelling that wrong. Okay, number 65. Find the constant a, or a and b, such that the function is continuous on the entire real line, so for all real numbers. So always start with the definition of continuity for this. So if f of x is going to be continuous, then the limit as x approaches 2 in this case, where the break in the graph would be, of f of x has to equal f of 2. So first of all, go ahead and find f of 2. So when x is less than or equal to 2, you plug it into x to the third. So f of 2 is 8. And the limit as x approaches 2 of f of x would be plugging 2 in for the x in ax squared. So you would get a times 2 squared. That's just a times 4. So if I divide 4 to the other side, I get a equals 2. If a equals 2, then this becomes a continuous function. The two pieces meet up at the same point. Same thing here. Remember, this expression needs to be simplified. X plus a, x minus a, over x minus a. So if you are trying to plug a into it to find the limiting value, you will be plugging into just x plus a. Knowing that, I set it up by definition first. The limit as x approaches a of g of x has to equal g of a if g is going to be continuous. So g of a is equal to 8. And this limiting value, we have to plug into x plus a. We don't want to just plug a into the original because we'll get 0 over 0. But if we simplify this a bit, we would get a plus a when we plug a in for x. So if 2a equals 8, then a has to equal 4. So if we go back and put in 4s for the a values, then we should get that the limit is equal to 8, just like the function value. Use the intermediate value theorem in a graphing utility. I guess I used a graphing calculator here to approximate the 0 of a function on the interval 0 to 1. Repeatedly zoom in on the graph of the function to approximate the 0, accurate to 2 decimal places. Use the 0 or root feature of a graphing utility. Okay, so this is like pretty kind of an unnecessary question, I think, when we're using Desmos. So let me just go ahead and use Desmos here. Here it is. So let's go ahead and type in f of x equals x to the third plus x minus 1. So what did they want me to do? They wanted me to zoom in on the interval 0 to 1. So the way to zoom to a specific window is that I've found is to add a table, put the endpoints of the interval in, and then just say like f of 0, f of 1. And once you fill in a table with 2 points, it'll zoom fit for you. So here's what the scenario that we're looking at. This looks like the 0. And the nice thing is on the graphing calculator, it takes a few steps to find a 0. But here we can just click near the 0, and the gray point that it highlights, that is the 0. So accurate to 4 decimal places, it's 0.6823. And that's the same as see how my graphing calculator did that as well? You're allowed to use a graphing calculator on the AP test. It's just that I'm switching to Desmos because it's easier and it's free. So it's kind of nice, and it's built into our test, so we might as well use it. All right, and yeah, you can repeatedly zoom in here to get an even closer look at what you think this value is. But again, you can just click on it. There it is. All right, what else do we have to do for this assignment? Let's see. 95. State how continuity is destroyed at x equals c for each of the following graphs. So for part A, there is a jump in the graph, but I don't want you to say that. I don't want you to say jump. I would say the limit as x approaches c on the left of f of x, let's assume this is called f of x, is not equal to the limit as x approaches c on the right of f of x. So the limit as x approaches c, maybe I don't even have to go into all of that, of f of x does not exist. So f of x is not continuous at x equals c. Maybe I wrote way too much there. I don't know. Why isn't there a discontinuity here? Because f of c does not exist. I'm going for shorter explanations here on these. Remember, our three things for continuity is the limit has to exist, the function value has to exist, and the limit has to match the function value. For part C, the limit doesn't match the function value. So the limit as x approaches c of f of x is not equal to f of c. And for the last one, same issue as part A. I'm just going to shorten this one up. The limit as x approaches c of f of x does not exist because, I guess I'm not shortening it up. I don't know. I just think it's good to practice this. The left limit doesn't equal the right limit. All right, I left my writing up for this one, so let me just talk through this. So it says, if functions f and g are continuous for all real x, is f plus g always continuous for all real x? So discontinuities happen if you have an x in a denominator, or if you have a piecewise function where the two pieces don't match. And I don't think either of those can just all of a sudden happen if you have two continuous functions for all real x. They don't have limited domains or anything like that. So that first part, yes, f plus g will have to be continuous. Is f divided by g always continuous for all real x? So f divided by g might not be continuous. So my example here was, okay, so if g of x equals 0 at any point, you get a discontinuity, right? So say f of x is x plus 5, g of x is x minus 3. On their own, those are two continuous functions. They're two lines. They're defined for all real x. But when I make it x plus 5 over x minus 3, now that function, that f divided by g function, is not continuous at 3. So that's just one example. And then just one true or false problem. So number 99 here, if the limit as x approaches c equals L and f of c equals L, then f is continuous at c. This is true because it's the exact definition of continuity. The limit at c is equal to f of c, and both of those are equal to L. L equals L. If you have any questions on this assignment, please come into office hours or ask me during class. We should have a little bit of time to go over things.